Our next talk is by Ngoc Tran, team Hash Brown, and they won second place in the competition, just slightly below the first winner. And the title of the talk and of the approach is Random Walk Rankings with feature selection and imputation.
Yeah, thanks very much, the organizer, for organizing this competition. My name is Ngoc Tran, and I'll talk about our method, which is random walk rankings with feature selection and imputation. And this is joint work with Xinyu. Right, so when I wrote these slides, I banked on the fact that since I'm the second speaker for this session, Harlan's team has already explained like the background of the problem, right? So I'll skip that part. So we go straight to our model. So our model is basically, we believe that the probability that two nodes will form a link in the future, that is some function of some properties of node U, some properties of node V, and then some properties about the neighborhood of the potential edge UV. Okay. So then our model looks like this. Okay, if you have node U and V and you want to know what's the probability that they form an edge in the future, then you look at the features of node U, all right, the features of node V, and then we kind of take the coordinate-wise min and max, just so that our feature vector is invariant under the ordering of the nodes, right? So if you put in UV instead of VU, it should give you the same set of features. Okay, and then finally we also compute something about some function that capture the neighborhoods of U and V. Right, I'll explain what that is in a bit, but that's the overview. So now once we have this vector, right? So now for each node pair, I have a big vector. Then I just plug in. It becomes a binary classification problem. We tried several things. For example, logistic regression actually works extremely well and would also have given us second place. But our best model turns out to be a ReLU network. It got 5 hidden layers and 13 nodes in each layer. And in the end, it outputs a probability. So how many features did we use? So this F, it turns out, maps from U to R31. So each node has 31 features. And then, so the two nodes give you 31 times 2 is 62 features, because I added up wrong here. 62 features are just the F part. And then the things about the neighborhood, in the end, we only use 2 features. Okay, so what are the node features? So overall, we have 64 features. So overall, our nodes features are things like, what everybody else used. So things that capture node popularity, like the degree, page rank. One thing we put in also is the number of papers. That is the number of unique timestamps that this pair of etched appear in the past, and we use that as a proxy for number of unique papers that this node has appeared in. So we have like about 10 of these features that are node popularity, and then we take the time derivatives. Right? So this is how we deal with the time component of the graph. You look at, say, degree at time t, degree at time t minus delta t, degree at time t minus 2 delta t. And for edge features, then we only have 2 numbers. One is dissimilarity, and this is like a normalized version of the number of common neighbors. Okay. The other one, which we found to be quite good, is hoprec. So this is called this is higher order proximity score. So it's basically a it's computed from running a random walk on the graph, and then hoprec will create an embedding of each node into, in this case, R128, right? So each node becomes a vector of length 128, and then the score of a pair UV is simply the cosine similarity between these two vectors, right? So hoprec is designed so that the embedding is such that if U and V is more likely to form an edge in the future, then if U and V are more likely to be neighbors, then the cosine similarity score is higher. So this is a single number, so is that. So altogether we have about 64 features. Okay. So how we trained? So we normalize time. So time runs between 0 and 1, right? And so we train at time t is 0.9, which fortunately I can't tell you what year that is. I forgot. Yeah. So we train at t equals to 0.9. We trained on 75% subsample of the data. So we found that you don't really need 75%. You can do reasonably well with just very few data. Actually, you can do with say 1% subsample. You get more or less the same results, just slightly worse. And our train validation and test scores are pretty good. So train validation is 0.9, and then the test scores is better. This is what we found for the for the test set, that somehow it seems to be easier from the viewpoint of the model compared to the training and validation. It's probably a good thing. So one thing, when we wrote down this model, there's the main issue of cold start. So cold start is the issue where you need to predict a future link between a node that involves a node that you've never seen before in your data set, in your trained data set, right? So here is an example. Say in my training graph, I saw these nodes, right? But then in the test set, I might be asked about, what is the probability that these two guys form a link in the future? With this node, I have no idea what it is. Same thing, right? Here, I have no information about both nodes involved in the edge, right? Now the problem is, my model said, well, probability of U forming an edge with V is a function of node features of U, node features of V, and something about the neighborhood of U and V. So if this is a node that appears outside of the training set, then potentially I don't know what's the node feature of this guy, right? Okay, and this is a serious problem in the test set. So in the test set, about 33% of the edges sort of look like this. We call these edges pirates because it's like you're blind in one eye, right? And then these are blinds. It takes up about 2% of the test set. These are when you truly blind in both eyes. Right? So what to do about cold start? We tried a few things, but what we found to work the best was just to impute, right? So in the intuition is, if I see a node that appear in the train, that appear in the test set, but not in the train, then that node appeared sometime between 2017 and 2020, right? So that node is a recently born concept. So its features should sort of looks like a recently born node in my train set, right? So that gives me this heuristic that the features of a node I see in the future is basically the average of the features of the newborn nodes, right? Where newborn are all the nodes that are born in the last time epoch of train. Okay, so that does that help us approximate FV. But what about the neighborhoods, right? So well then, if in the pirate case where I see one node U but I don't see the node V, then by an extension of this logic, right? What's the say dissimilarity score between a node I've seen and a node I haven't seen? Is that should just be the average of the dissimilarity score between the node I've seen and the set of recently born nodes, right? The set of newborns. And same thing if in the blind case, then HUV is just the average over all possible say dissimilarity of all possible pairs of newborn nodes. Okay. Okay, so just a recap. So that's our model. So we're imputed, and then we have a just did a vector embedding plus a binary classifier, and yeah, and we tried a few things. So I think it's worth noticing that hoprec alone. So hoprec is a very well-known method in recommendation systems. And for a while, it got like the best performance in collaborative link prediction, which I think is a very similar problem to this one. So hoprec alone would give you a test AUC of 0.89. This is just hoprec by itself. Don't just take the hoprec score and plug that directly in as the predicted ranking. You get 0.89. So what we did different from hoprec is we had this extra dissimilarity and another 62 features of the nodes, right? And we have a binary classifier on top. So doing this, if you just use logistic regression for a binary classifier, very simple, then you get 0.925, right? And anything else we do on top of that is replacing logistic with a slightly more complicated binary classifier, right? So we tried MLP with various architecture. We try adding on, other scores similar to HopRec, but it's just not a. I mean, it's good, but it's not a massive improvement. And we tried training MLP with dropout. We tried a little bit of GraphSage, graph convolution. But those, I mean, they're all good. They're all give scores between 0.925 and 0.927. But the final model, we find the best with just an MLP. Okay, that's it. That's all I have. Thank you for your attention.
Thank you very much. That was very interesting. And I found especially interesting that you were very much focused on these problems of nodes that have not appeared before. I love that you call it pirates. That's awesome. I will definitely use that word also. There are a few questions, but maybe because I started to mention this already, I think this was kind of not intentional in the data set. We only saw it after we started the competition. And I think it was probably very important that you investigated and used the method imputation. So my question is, did you actually look into what happens if you don't use this method, if you ignore that problem?
Yeah, like if you don't impute,
yes.
If you don't impute, you get like 0.90 something, right?
Yes.
Without imputing. But I should notice that is on the 2014 data set, right? And but that somehow turned out to be a more difficult data set compared to 2017, like the actual, like the train data set you supplied. I think that's somehow slightly harder. So I would expect something like 918 or whatever, but actually the very first, maybe we had a 918 at one point without imputing. Yes.
918.
918. Yes.
Okay, so that would have been the third or fourth place, right?
Yeah, something like that, right? Okay. So it's not terrible, but I think like 918 compared to 927 is quite a big gap. Yeah.
Yes. Okay, that was very interesting. There's a question by Michael Kopp now. Great approach with regard to taking the min and max components twice of the feature vector f of u and f of v for two nodes u and v. Do you have an indication how much the performance has enhanced by taking these operations?
What, taking this min and max?
Yes.
Yeah, well, I just for the fact of, I want a model that should be invariant under node permutation, right? Just because I don't want the model to output different things if I query, node 1,2, sorry, h 1,2 versus h 2,1. So I think right from the beginning, we did this min and max. And I should notice that this is not, it doesn't throw away any information, right? If you have two numbers, a comma b, and if you know the min of a and the min of the two and the max of the two, then you still, it's just like a non-linear transformation, but it's a perfect one-to-one transformation. So, I don't think we lose very much. Well, we don't lose anything. And we just started out doing this straight away. So I cannot tell you if you don't do it, what will happen, at least for the purpose of, having a model being consistent with itself. Then if you don't do it, then you have this issue that, the prediction for u comma v is not the same as the prediction for v comma u, and that's kind of not nice. Yeah.
Okay. Harlan Lee just made a comment, I think, on your first statement, why the dataset 2014 was maybe more difficult. She said maybe because the 2014 graph is sparser than the 2017. Do you think that could be the reason?
The 2014 graph is what? Sorry?
It's more sparse.
It's more sparse?
Yes, and I think you have more pirates and blind.
Oh, you have way more pirates. That's right. You have way more pirates than blind. You have something like 50% pirate, 25% blind, and 25% signal or something like that. So I think that's difficult. Is it more sparse? I think it's because like the features are a bit less stable. So yeah, so that could be related to sparsity. Like for example, some of the features we use are like, compute, like how the degree has been growing over time, right? So if you have nodes that kind of prop up a lot of the nodes by 2017, 2014, a lot of the nodes have actually crop up relatively recent. So their derivatives don't tell you much. So that I think is an issue. Yeah.
Yes. Okay. And also, uh, your Montino, he also said that 2014 has a lot of pirates that could be the issue. So yeah,
Oh, by far. Yeah, that's right.
yeah,
Initially we did train like 3 separate models, one for the scene, one for private, one for blind, and individually they perform well, but it's just when you combine them, then they perform badly. And I think it has to do with well, I have some ideas about why that is, but that's partly why we settled with imputing.
I see.
Yeah.
One approach against the problem of different ratios of the pirates and blinds is to adapt the data set in the 2014 case. Did you play with that? So to kick out a number of pirates such that you have the same distribution of pirates compared to normal vertices as you have then for the 2017 one.
Right. Yeah, I think generally you would like your train set to look like your test set, right? So if your test set has 50% pirates, then you want to like upsample the pirates a little bit during your training. Yeah, we did a little bit of upsampling of pirates over here as well. Yeah.
Okay. So there's another question by Michael Kopp. It is interesting that your feature H, U, and V when using Cobrac dice were so successful. Why do you guess that this random walk similarity score seems so important? Yeah, that's a very good question.
Yeah, this Hoprack by itself. Yep.
Yes.
Yeah, sorry, but what is the question?
It is in so Michael is wondering why the Hoprack dice feature is so successful.
Oh, why is it? Oh,
Yes.
it's not surprising at all. I think like Hoprack, it is a well-known method that does well. So what it does is just like it does a random with like Hoprack is it's quite sophisticated, I would say, right? It's a method that if the goal is to learn an embedding, right, such that the probability of you making a link with V, right, is proportional to the inner product between the embedded vector, right? So Hoprack already is solving a version of this, right? Hoprack is solving a version just without the HUV. Hoprack model is literally probability of U total V is some function of FU/FV. Its goal is to learn F, right? And the way Hoprack learned F is using well, it writes it down as an optimization problem, and it's doing a random walk to try to compensate for the lack of this term, right? So yeah, so I think Hoprack is much more sophisticated than, let's say, number of common neighbors, because that's like degree 1 features. Hoprack can take information that are by running like a local random walk, it can take information that are like degree 3 or 4 away, and I think that's really important. Yeah.
Okay. When you showed your table of different models that you were using, I was kind of surprised actually that basically the simplest MLP worked, and for instance, dropout didn't help you, or other techniques. Do you have any idea?
Oh, like why is the simplest one works well?
Yes. Is it because of the training data, or yeah?
Yeah, I think fundamentally this data set is large, but it's not rich, right? In the sense that the node features are things that you kind of derive from the graph topology. And that's, there are lots of things that you could derive, but they're all quite correlated, as you know, several talks have pointed out. So I think when the features are not rich, then there's a trade-off between well, there's always a tendency that you could overfit, and so simpler model by design is like regularized. So it helps in that aspect. Like having more features just kind of lead to overfitting. Like if you look at if when we look at like our train and validation score, this MLP is definitely not the best in terms of training and validation. It got like 906 in training and validation. We totally have models that get to like 91 something and 915, but somehow in test they just don't perform as well. Yeah.
I see. Okay, there's one comment by Xin Yu. The hop-rec embedding we used has a random walk of step 5 for each node. So it learned, is it? Okay, so it learns the local neighborhood of each node. And it includes a lot of information captured by indices such as Adami score and common neighbors.
Yes, absolutely. Like we find like hop-rec by itself just awesome. Like
Yes.
the rest of the models are, I mean, it helps to bump from 8-9 to to being in a winning position, but it's very good.
Yes. Okay, so let me see. I think I missed one question. Yes, there's a follow-up question by Michael. If you allow for a follow-up question, yes, I allow it. Would you think hop-rec would work well on general types of temporal graphs, or did the sparsity here make a difference? Okay, that's very interesting. Yes.
Oh, sorry, I didn't quite understand. What about?
So Michael is asking whether you think that hop-rec could work on more general temporal graphs, dynamic graphs?
On dynamic graphs. Oh yeah, like we definitely thought about like turning hop-rec into like a temporal model. I think that's a very interesting question, and I love to see. I think it's not hard to take that objective function and slap on like a temporal term. But like we didn't have time to try, but I think that's for a research direction. I think that's a really, really good comment. Yeah.
Okay. There's I think one more comment by Hinchu about we use a temporal trunk. Okay. That's about their approach. They used actually temporal truncation on top of hop-rec, but it was very coarse truncation. Okay. Okay, so I think that was no. I wanted to ask how much time did you need to train your model, actually?
Oh, not much at all. Like I think we have a CPU. It's actually like a server I bought in like 2016 or something. So it's very like ancient in terms of technology.
Wow.
It didn't need much time at all. Like it's like from start to finish, I run it. This doesn't like within 10 minutes. I think it's from taking the raw data all the way to spitting out a number. It's about 10 minutes. Yeah.
Okay,
Yeah.
wow.
But that's assuming that the hop-rec has been pre-computed. Hop-rec takes a long time. Like it takes maybe I would say maybe like about half an hour to produce those embeddings. But yeah.
Okay.
Yeah.
Okay, cool. Very interesting. So thanks a lot again for your contribution. That was very interesting. Congratulations for second place. And yeah, hope we stay in touch. Thanks a lot.
Thank you.